I'm Samuel Mergendahl. I work at MIT Lincoln Laboratory. Today I will be presenting our work titled Cross-Language Attacks, in which we present a new attack methodology to be able to circumvent many commonly deployed defense mechanisms. Our work investigates the new paradigm of multi-language applications, or MLAs. These are applications that deploy in multiple different programming languages inside of one application. Unfortunately, we show that because these different languages may choose to deploy different defenses, their defenses may have inconsistent threat models which may lead to new attacks. In particular, we introduce cross-language attacks that take advantage of these inconsistencies. For example, below, we see an MLA that consists of Rust and C code, where Rust deploys memory safety and C deploys control flow integrity. As the program executes, the control flow may transfer from Rust into C, in which inside of C, we may run into a bug that consists of a memory corruption bug that can be used to corrupt indirect jump or something else in the Rust control flow later on in the program. So when the attacker reaches this corrupted indirect jump, it can then transfer and start to execute its weird machine. So what really happened here is that there's this inconsistency of threat models where C deploys control flow integrity but not memory safety, and Rust deploys memory safety but not control flow integrity. So in order to get to the origin of some of these various defenses, we can see that throughout the last few decades, many actual defenses have been proposed, but unfortunately, they're always typically followed by some other advanced attack. So this eternal war has sort of led to a tension that can keep the observed CVEs that we actually see sort of stagnant. And you can see in this graphic in the middle that from between 2006 and 2018, around 70% of all the CVEs reported at Microsoft were related to memory safety. And actually, these statistics are also reported by other companies such as Google. So alternatively, some believe that new, safer programming languages can be a catalyst for real change in this eternal war. And that's because they have this ability to have memory safety guarantees without insane performance costs. So two examples of this new safe programming languages are Rust and Go. They both have strong type systems that can facilitate many of the needed compile time security checks, such as preventing arbitrary casting, but they also include proper runtime checks for dynamic data. Both of the languages provide temporal safety, just with different strategies. So for example, Go uses garbage collection, whereas Rust uses lifetimes and ownership. The main point for our work, however, is that while these runtimes are different and they're both considered small enough to be acceptable in the systems domain. Unfortunately, though, there's about 50+ years of unsafe legacy code out there that we can't just immediately rewrite in these new programming languages. So these languages then have to have flexible and strong foreign function interfaces, or FFIs, that allow for actual interoperability between other languages. This is going to be able to then facilitate incremental deployment into these legacy code bases, and this is what we really call the multi-language application. So in fact, this trend is actually pretty common in industry, and we can see that with many different applications like Firefox or CockroachDB. And so while we fundamentally support the incremental deployment of safe languages, this work demonstrates that if you don't do it carefully, the incremental deployment can actually reduce the security of your application. So in particular, as you'll see today, we create a graphical model to represent this new paradigm of multi-language applications and show that many variants of our cross-language attacks are possible in this new setting. Of course, we're not going to be able to discuss everything, so we encourage the listener to seek further details in the paper. So in order to set the stage of our attacks, we're going to sort of highlight some of the details of Rust safety guarantees. The main driver of Rust safety is that it forces mutation XOR aliasing. So you can have a program that mutates data or aliases data, but you can't do both at the same time. And so you can then, the sort of two sides to this are ownership and lifetimes. So with ownership, you can pass by value to a function to transfer the ownership, or you can pass by reference to temporarily borrow the ownership. This borrow can be mutable or shared, where a mutable borrow, you guessed it, you're allowed to mutate and not alias, but with a shared borrow, you're allowed to alias but not mutate. So the temporary nature of these borrows are then described through lifetimes. So after a lifetime of a variable ends, Rust can perform automatic memory management to free the variable. Additionally, Rust leverages what is commonly referred to as fat pointers that associate metadata with data to prevent spatial errors as seen below with the vector type vec in Rust. So in fact, on the right, we can see a simple Rust program that creates a vec, borrows the data to other functions, both through mutable and shared references, and finally transfers the ownership to another function. After the ownership transfer, Rust can no longer borrow or use this data. So for example, line 18 would cause a compiler error in the program. We also see the discussed spatial and temporal guarantees in this example. Lastly, I just wanted to mention that in order to actually be usable in the systems domain, Rust has had to allow sort of an escape hatch from its strict type system. This is going to be able to facilitate things like performance optimizations or other low-level device management. But for our work, it's important to note that while Rust forces the unsafe keyword for FFI calls, FFI really only describes the intended interaction that the languages are supposed to have. So this one line of unsafe Rust code actually opens the door to many other unintended interactions between the languages where they're able to influence each other through things like their shared address space. So to get an understanding of how this relates to multi-language applications, we first observe the threat model of a C program that has no defenses on it. An attacker will start an execution, try to corrupt some memory, inject some gadgets, hijack control flow, and eventually try to execute a weird machine. So one approach to prevent this attacker flow is to harden C with a defense like control flow integrity, or CFI. And this defense is really aiming to remove that control flow hijacking block from the attacker's path. And of course, as we've seen in recent literature, that there are also data-only attacks that this isn't a perfect solution, but at least we're hardening the C threat model. So on the other hand is the threat model of safe languages that are really trying to remove that first memory corruption node to prevent all possible attacks for the attacker to get to that weird machine. So our work shows then, unfortunately, when you combine these two threat models together, you get a new language transfer node. And so we can actually see that we end up in a place that's about the same as when there was no defense added at all. An application can start in C, use the new language transfer node in the attacker's path to move over to the safe language, and then follow through with the control flow hijack. So therefore, while we kind of get to this conclusion of when you add something good, like notably a safe programming language, to something that's historically kind of struggled, like hardening with C, you might actually leave us with something that's worse. So next, we extend our threat model into a descriptive graphical model that can represent many forms of our cross-language attack. So as you can see, this model contains some of the basic blocks from the previous page, just with additional details. So for example, with our model, you can overlay particular defenses, like CFI or shadow stacks for C, C++, or lifetimes, the borrow checker, dynamic bounds checks, things like that for Rust. Additionally, our model is hierarchical in that you can take one of these nodes and zoom into it so you can concretely describe some of the defense details in either of the languages. You can look at where lifetimes are or the dynamic bounds, etc. Moreover, our model is expressive enough to overlay specific attacks, such as the one presented in a recent TOPS paper, actually, that is similar to our motivating example from before. And this facilitates a very clear visualization as to how an attacker can bypass deployed defenses. However, the critical advantage of our expressive model is that we can also use it to identify other cross-language attacks. So one such variant that we describe in the paper is how to corrupt Rust safety guarantees, spatial safety guarantees. And so here we have a simplified code example where Rust creates a vec and then calls a C function, but the C function contains an out-of-bounds error on line 8. So thus, we can use this memory corruption in C to overwrite the fat pointer associated with the vec in Rust memory. This leads to cascading spatial corruptions as the dynamic checks in safe Rust will now fail to end up identifying these out-of-bounds errors that, like you can see on the Rust side of the code on line 8. Similarly, we can corrupt the temporal safety of the guarantees in Rust. In particular, we show that an example on here is with some more code again, where a C function mistakenly frees a pointer that's actually associated also with Rust data, and this is going to cause incorrect lifetime calculations in Rust. So at the free, this will lead to a use after free on line 6, as well as a double free after the Rust function completes. So given these cross-language attacks, we want to identify how frequently their primitives actually appear in real-world multi-language applications. So in particular, we have two main research questions. First, we want to see how often language transfers actually occur in the program. And second, we want to understand if language transitions are widespread towards a diverse set of functions or sort of limited towards a select set of functions. And we perform this evaluation on Mozilla Firefox, as it is a large, well-known open source code base that happens to also be a multi-language application. So to answer our research questions, we define a set of metrics related to language transitions. First, we define call sites as a function that calls another function. And as a subset of call sites, we are interested in transfer points that are call sites that cross the language boundary. Similarly, indirect and dynamic calls are a subset of call sites and are building blocks for CLA variants. Similarly, we're interested in the behavior of invocations, which are when a function is the callee of another function. And in particular, we want to visit what we call visitor points, which are, again, that subset of invocations that are crossing that language boundary. And finally, we'll end our evaluation with the discussion of the distribution of language transitions across functions to identify any heavy hitters in this distribution. So to start with our call site analysis, we present the following table where each cell contains the raw magnitude that we collected, as well as the column and row percentages of its subclasses. For example, we found about 12,000 transfer points in Rust functions, and of all the call sites in Rust, just over 3% of them are these transfer points, and just over 5% of those transfer points are in the entire binary come from Rust. While these percentages are small, we note that the actual magnitude is still quite large. 12,000 is non-trivial. Moreover, we see that many of the building blocks needed for CLA in Rust are inside of Rust functions, such that over 50% of many of these Rust indirect calls are for call sites, and over 38% of all Rust call sites are dynamic calls. And in fact, this behavior is unique to Rust when compared to C++ code. For our invocation analysis, we see that the majority of Rust invocations come from memory unsafe languages, and additionally, most language transitions actually go from C++ to Rust. From this, we can conclude that Rust is mostly acts as a service module for C++, which is notably in line with this paradigm of multi-language applications and incremental deployment. Finally, for our heavy hitters analysis, we see that while most language transfers were actually towards Rust, when Rust does call a C or C++ function, it's most commonly referred to or associated with libc. This makes sense as the Rust standard library is actually built on top of libc, and in particular, we posit that this is a fruitful area for future defensive work against CLA attacks. So in summary, we investigated a new paradigm of multi-language applications where we presented a graphical threat model and demonstrated that many different languages have incompatible assumptions. And in particular, these assumptions may lead to variants of our cross-language attacks where attacker maneuvers between languages to circumvent deployed defenses. Lastly, we demonstrated that the existence of many building blocks of CLA actually do exist in real-world multi-language applications, and we distribute all of our code as open source, which includes our evaluation metrics as well as a number of more complex proof of concept code examples that compile real code and show that this is possible. So thank you. Any questions?